In this video, we'll be talking about the remainder of the alternating series. In previous videos with remainders, we're specifically trying to determine what the value or how is R sub n bounded. We're really just talking about, well, what terms does R sub n have to be then less than, or how can we determine the overall inconsistency or inaccuracy of the summation or the approximation that we've taken. So in this case, when we're talking about this, we're talking about this remainder using -1 to the power of k plus 1 times some other function a sub k. So this is an alternating series such that, again, a sub k still has those two very specific properties. It is always, again, not increasing for every individual term, as well as the limit of a sub k will equal to 0. So, with this particular statement being made, we can go ahead and look at the fact that since it's non-increasing, or all the terms are decreasing, R sub n would have to be equal to, in some way, by definition, this. And again, keep in mind that this is the infinite sum minus the sum of the first n terms. So this is the definition of the remainder. It's what is the exact value minus the set of values that we've removed. What are the remaining values that are left? Well, we know this has to be less than or equal to the absolute value of Sn plus 1 minus Sn. And again, the reason for this is the fact that since every individual term magnitudally is always decreasing or the same, this either has to be equal to this value, because again this term is going to have to be equal to the term that we're adding, or overall this term has to be greater than this remainder, specifically because again this is absolutely going to be a value that is, again, smaller than or close to it based on the fact that we're alternating it. Well, if I subtract these two values from each other, I end up with a sub n plus 1. So in this case, we know R sub n has to be less than or equal to, well, the next term in the sequence. So this is the actual theorem for the remainder theorem. It states the remainder is less than or equal to the magnitude of the first neglected term. So again, keep in mind that S sub n is a1 plus a2 plus ... all the way up to a sub n. So these are the first n terms that we added up. Well, the remainder will definitively be less than or equal to the first term that we didn't include in this summation. So that's the actual theorem for the remainder in the alternating series. So when we work through this, it's just a matter of, well, working with that last term. So in this video, we're going to go ahead and do an example with this. We might as well. So the example is the natural log of 2 can be approximated using this series. Now this is going to come up in later videos in terms of how we approximate it and why we approximate it, and the general understanding of how is it that this thing is going to turn into what it is. Well, let's just start with the fact that this is approximately this series, which is actually an alternating series. It is the alternating harmonic series. So this is what it really equals to in an infinite number of terms. Well, given that this is an alternating series, again, with 1 over k always being, with 1 over k, the second statement, the limit as k goes to infinity of 1 over k equals to 0, and with the detail that if you take the derivative of the a sub k, you do have non-increasing values. So this is an alternating series, and after making that conclusion, we can then go ahead and start talking about, well, what is the remainder, or how many terms do we have to add up before we can guarantee that we have the remainder within a certain value. So the question in this particular case is I want to make R sub n less than or equal to 10 to the negative 6. Okay, what I'm saying is I want the remainder accurate, or I want the summation accurate within 10 decimal places or 6 decimal places. So how can I make this happen? Well, first of all, I know R sub n has to be less than or equal to a sub n plus 1. I do know that with this particular series, a sub n is equal to technically 1 over n. So when I'm looking at a sub n plus 1, I know that a sub n plus 1 is actually equal to 1 over n plus 1. So I know that this thing is equal to 1 over n plus 1, and the statement ends up revolving around the case that I know this thing is equal to this thing, I know this thing has to be, or this thing is less than this thing, but I want this thing to be less than this thing. So the way that we're going to arrange these details is I know that this R sub n is going to have to be first. R sub n is less than or equal to something. The next statement is I want it to be less than this, but I know it's less than this. So if I force what I know it's less than to be actually less than or equal to the thing that I want it to be less than, then this is definitively less than this by the definition of a remainder in a theorem, remainder in an alternating series, and then therefore by making this forcefully less than this, I know that the remainder is then also less than that value as well. So this is really what I'm going to be working with. I'm going to just go ahead and solve this little minor equation. In doing so, I have 1 over n plus 1 is equal to 1 over 10 to the 6th. I will change that negative exponent to be a positive exponent. I'll multiply both sides by the common denominator, giving me, less than or equal to. I'll multiply both sides by the common denominator, giving me 10 to the 6th equals n plus 1. So I know, less than or equal to. So I know that n has to be greater than or equal to 10 to the 6th minus 1. And that's what we're looking for. So the question is how many terms do I have to add up? Well, it's 1, 2, 3, 4, 5, 6 minus 1, it's quite a few terms. This particular alternating series does not do an efficient job of approximating the natural log of 2 because of the number of terms we have to add up just to get this thing accurate within 6 decimal places. Seems like it's going to be, again, out of the range of things that we want to work with. Again, the concept for a lot of this stuff is really for us to try and find a way to approximate these values where we don't have to have we can have a computer run the numbers for us and us not having to create an entirely new program. We can just go ahead and create a series and have the computer run the program to evaluate it. But then again, this one doesn't work as efficiently because of how many terms we're going to need to tell it to add up before it's accurate within 6 decimal places.